This video is an introduction to population genetics and using the Hardy-Weinberg formulas to calculate population parameters. So genetics on a population level is going to be important in measuring microevolution. Microevolution is the change in allele frequencies in a gene pool over time, where an allele is a version of a gene, so either dominant or recessive, and the gene pool is all of the alleles for a given gene in a whole population. So the frequency of an allele can be calculated relatively easily. Remember that diploid organisms are going to be carrying 2 copies of each allele. So if there were 100 individuals in a population, there would be 200 alleles for a given gene. So if I wanted to determine the number of dominant alleles, what I would do is just multiply the number of homozygous dominant individuals by 2, because each of them has 2 copies of the dominant allele, and then I would add the number of heterozygous individuals, because each of them just has 1 copy of the dominant allele. Same logic applies to recessive alleles. If I wanted to calculate the total number of recessive alleles, I would multiply the number of homozygous recessive individuals by 2 and add to that the number of heterozygous individuals. Okay, so let's do this. So let's say we're looking at a population of cats and we know that there's 36 homozygous dominant individuals, 48 heterozygotes, and 16 homozygous recessive individuals. So it's pretty straightforward to calculate the frequencies of the recessive and dominant alleles. So let's do that together. So here's the same problem. So we've got 36. So let's see. First, we're going to try to calculate the number of big B's in a population. Then we'll calculate the number of little b's. So for big B's, it's going to be the number of homozygous dominant individuals times 2, because each of them has 2 of these big alleles plus 48, because there are 48 individuals who are heterozygous. So they're each carrying 1 of these alleles. So I would add these 2 numbers together and I would get 120 big B's in this population. For little b's, I'm going to take the number of homozygous recessive individuals, multiply that by 2, and then again add the number of heterozygotes. Each of them just has 1 allele, so I'm just going to add 48 to 2 times 16, and that is going to give me 80. So 80 plus 120 is 200. That makes sense. There's 200 alleles in this population of 100 individuals because each individual is diploid and carrying 2 alleles. Okay, so with Hardy-Weinberg, we're usually interested in P's and Q's, and those aren't the number of the recessive and dominant alleles, they're the frequencies. It's pretty simple to calculate P. That's just going to be 120 divided by 200, where P is the frequency of the dominant allele. It's pretty easy to calculate Q, which is the frequency of the recessive allele. That's just going to be 80 divided by 120, or I'm sorry, divided by 200, which is 0.4, and P is 0.6. So in our population of cats, we know the number of these dominant and recessive alleles, and we also went ahead and calculated the frequency. So now I want to go back to this presentation and show you how we can use the P and Q, the frequency of the dominant and recessive alleles, to determine the frequency of the genotypes. So here I'm using a population level Punnett square. And in this square, what we have is the chance of a allele, two dominant alleles being found in the offspring. So that's 0.36 or p squared. In this square, I'm showing the chance of the offspring inheriting one big and one little b. So that this would be a heterozygous individual. And there's two different ways in our square that that can happen. And p times q is 0.24. So I've got 0.24 here and 0.24 here. And then in this square, I'm showing the chance of an individual inheriting two of the recessive alleles. Those were coming at a frequency of 0.4 in the population. So 0.4 times 0.4 is that frequency, that genotypic frequency, and that's 0.16 in this case. So you learned in the Amoeba Sisters video that there's two Hardy-Weinberg formulas, and this is where the second one comes from. P squared plus 2pq plus q squared equals 1. These frequencies add up to 1, and p squared represents the homozygous dominant genotype, its frequency. 2pq represents the frequency of the heterozygotes, so 0.48 if we add these two up. And then q squared represents the genotypic frequency of the homozygous recessive individuals. So we can use these two formulas to solve genetics problems. The Hardy-Weinberg formulas are assuming that no evolution is happening. So these frequencies did not change from one generation to the next. So we started with 36 out of 100 homozygous dominant individuals, and we see in the next generation it's the same. Started with 16 out of 100 homozygous recessives, and we can see that that frequency didn't change. So this population is within Hardy-Weinberg equilibrium. That's not really common. That would require these assumptions being met, that there's no genetic mutations, there's no that there's only random mating occurring, that there's no natural selection, that the population is sufficiently large, and that there's no gene flow or migration. So for all these, if all these assumptions are met, there's no evolution happening, and we won't see changes in gene frequency, just like we did in the cat example. But in reality, these conditions are rarely met. Hardy-Weinberg equilibrium is kind of a null hypothesis, something that we can compare the frequencies that we're actually seeing over generations with, so that we can measure how much evolution is occurring in the population. So let's look at another example, which is a little bit more like the ones that you are going to see in the problems that we do together in class. So this one involves violets, and let me pull it up here. So in plants, violet color, I guess this is of flowers, is dominant. So it's big V, represented with big V here, and white color is recessive. So to be white colored, they would have to have two copies of this recessive allele. So if Q equals 0.2, and remember that Q is the frequency of the recessive allele in a population of 500 plants, how many individuals would you expect for each phenotype? Okay, so determine which equation you would use, figure out a value you can determine, use the value from the previous step to solve. Well, I already have Q, and that makes it pretty easy to determine P using the Q plus P equals 1 equation. But I think I can actually do this really simply using the P squared plus 2PQ plus Q squared. So that's the equation I'm going to use to solve this. That's supposed to equal 1. So what I see here is that if Q equals 0.2, then Q squared is going to equal 0.2 times 0.2. And that's going to be 0.04. And remember, Q squared is the frequency of the homozygous recessive genotypes. So I already know how many individuals are going to be white, or at least the frequency is 0.04. So if I multiply that by 500, because I know there's 500 plants in this population, I'm going to get 20. So 20 individuals are going to be white. Everybody else in this population is going to have violet flowers. So I could either use this formula and determine that p squared plus 2pq is 0.96 and multiply 0.96 by 500, or I could just subtract 20 from 500 to determine the number of individuals that have violet flowers. So that sounds a little bit easier to me. So we have 20 individuals that are white. That means everybody else in this population is going to have violet flowers. So that would be 480 individuals with violet flowers. So there's a bunch of ways that we can manipulate these two formulas in order to solve these kinds of problems. Please let me know if you have any questions about this content.